Hello everyone, my name is Benjamin Lee. I'll be presenting our work on an immersive visualization animation grammar called Deimos on behalf of my colleagues listed on screen. One of the goals of immersive analytics is to use engaging embodied tools for data understanding. Existing works have explored the use of embodied interaction techniques to manipulate immersive data representations as though they were real objects. For example, TiltMap by Young et al. Clearly demonstrates how an embodied interaction technique can be directly mapped to changes in a visualization state. The use of animation facilitates changes between the three visualization types. Existing animation research has focused primarily on the design of the animation itself, however, and not on how it can be controlled or manipulated by the viewer. Even so, animation research in immersive analytics has been sorely lacking. Many works do not intrinsically focus on animation design, instead using it as a byproduct of some other form of action. In our previous work at CHI 2022, we presented a design space for how immersive visualizations can be transformed between 2D and 3D. A core part of the design space was the user interactions used to perform the transformation. However, it focused only on their design and not on how they can be created. In this work, we continue by introducing Deimos, a declarative grammar for authoring dynamic, embodied immersive morphs. What you see on screen is a morph that unstacks a 2D bar chart into a side-by-side 3D bar chart using an extrusion interaction. Here is another example. As the user pushes a 3D bar chart into a wall, it partitions into a faceted 2D bar chart and repositions onto the wall. Pulling it off the wall undoes this. That bar chart morph demonstrates two of our three design goals. First, morphs are adaptable and dynamic. This 3D bar chart was just a regular 3D bar chart. However, by pushing it into a wall, the morph is dynamically applied to it. Second, morphs support embodied interaction. This type of hand interaction is made possible with immersive technologies. Our third design goal is simple. We want to support conventional animated transitions as well, such as using familiar sliders. These morphs demonstrate two contrasting approaches to animated transitions. The conventional is data-driven. Animations are designed to showcase some particular aspect of the data, with the viewer having little to no control. Our new approach is interaction-driven. Animations are dynamically applied to visualizations at runtime in response to user interactions, assuming the correct conditions are met. The user can then decide when and how to use the morph by performing the interaction. These two approaches are facilitated by our grammar being dynamic. It can be set up to work with specific interactions and visualization configurations, or be applied more generically to any 3D bar chart regardless of data variables and dataset. Now let's briefly go through how the grammar works. We begin with a visualization layer. In this case, it is DXR by SIGCHI et al. DXR uses JSON specifications linked with datasets to create visualizations in Unity. Deimos sits on top of this as an animation layer. Deimos first loads all of the morph JSON specifications. It then keeps track of each DXR visualizations as they update. Depending on their state and user inputs, Deimos applies morphs to the DXR visualizations. So then the question becomes, what are these morph specifications? Morph specifications are written in JSON and follow the declarative Deimos grammar. Here is an example of a very simple morph and its specification. It changes the color of any visualization with spherical marks that are uncolored to red. This occurs whenever the left hand performs a select gesture and not the right hand. A morph specification consists of three components: states, signals, and transitions. Let's now go through these one by one. First are the states of the morph. These are best thought of as animation keyframes. Here we have one state for the base unhighlighted state, and another for the highlighted state. Unlike regular keyframes, however, they can be partially defined. Remember that we apply these morphs dynamically to existing visualizations. Thus, these states function as a set of properties that a visualization must have to undergo the morph. In this case, these two sample scatter plots are considered to be in the unhighlighted state, as both have sphere marks with no color encoding. This is in spite of the two using completely different datasets. This bar chart, however, does not match as it has cube marks with a color encoding, and thus cannot undergo the morph. Note, however, that this highlighted state has a restrict true parameter. This means that a visualization cannot match with it and start at that state, but can only transition into it. Second are the states of the morph. They are best thought of as streams of data that emit values based off user input. The values from these signals can then be referenced elsewhere in the morph specification. In this example, we define a signal called left hand select. We specify its source as the hand with left-handedness. We then choose the select value to be extracted from this hand, which is the pinch gesture that you can see. This signal will return true if the hand is pinching and false if it isn't. Third are the transitions of the morph. Transitions are what actually connect the aforementioned states together to allow animations to occur. We first specify which two states to connect together. In this case, we declare the names of our two aforementioned states, in the order of start state and end state. We then optionally state the trigger for this transition. This is basically the condition that must be true for the transition to actually begin. In this case, we use the signal that we declared to have the transition start when the left hand pinches. Lastly, we add some additional parameters to refine the transition's behavior. We specify a timing value of 0.25 seconds. We also make the transition bidirectional, meaning it can occur in reverse. When we put this all together, we can see that this forms a state machine. The state machine diagram is color-coded with the specification. If a DXR visualization has a sphere mark with no color, it enters the unhighlighted state. When the left hand starts pinching, it enters the transition for a time period of 0.25 seconds and ends at the highlighted state. When the left hand stops pinching, it re-enters the transition in the reverse direction for another 0.25 seconds and ends at the unhighlighted state. If at any point the DXR visualization specification is modified outside of this morph, such as through a GUI, it leaves the state machine. It may then immediately re-enter if it matches the unhighlighted state again. If it doesn't match, then it simply doesn't re-enter. And that is at its simplest how the Deimos grammar works. It listens for changes to visualizations and applies morphs to visualizations based off user inputs. Deimos itself can be found in an open source GitHub repository. The link is included in the paper. In the repository, you can find other examples that you can try, such as this configuration of tilt map. Detailed walkthroughs on how to use the grammar are also included. Lastly, the paper included an expert evaluation by 6 fellow immersive analytics researchers who you can see on the screen. We got them to use Deimos for at least 4.5 hours and interviewed them afterwards. They reported that Deimos did in fact have a steep learning curve, especially as they had to learn both a visualization and an animation grammar. They did, however, see the potential in the grammar in expressing new animation and interaction designs. Some proposed a GUI to simplify this authoring process, along with suggestions on how to do so. Some others also saw potential in using Deimos for prototyping their own research ideas. Of course, please see the paper for full results. And thank you all for listening, and special thanks to the 6 researchers who participated in our study.